Now, B part 5, Lie derivative and Killing vectors. I would like to say that this lecture, 21st, will be the last lecture. We'll complete the part 5, Lie derivative and Killing vectors. Now, lecture 21st, the sphere of unit radius. You see, we already derived for this sphere that we obtained the killing vector u. You see, that's important. I will use this just to show the conserved quantities using the previous lecture 20. Now, set up. Consider the spherical coordinates. You see, theta is a polar coordinate between 0 and pi, and phi is azimuthal coordinates between 0 and 2 pi. The flow is a tangent vector. The flow is the same as we write phi of t. Okay? There's the flow. Okay? So, the flow, the tangent vector to the geodesic is V is theta dot and phi dot. You see the derivative of theta with respect to t. T is the parametrized parameter. Okay? So, for the previous lectures, see, lectures, not lecture, the vector u is u theta. This is a basis vector, partial theta, partial phi, and u theta and phi are the components, where u theta is equal 0 and u phi is equal 1, as we derived in previous lectures. You see? So the vector u is just partial of partial phi. You see? We derived this. This is ready. That's just to use here. So the standard metric on this sphere is ds square is z theta square plus sine square of theta d phi square. Remember that we are working the unit radius. So in this case, dr square is 0. That's why ds square is applied to the surface, the sphere surface. That's it. If you compare, you see the metric g theta theta is equal 1, g phi phi is sine square of theta, and this is symmetric. Okay? The sphere, it has orthogonal basis. That's why this metric, the symmetric, they are symmetric, which is 0. So, for the previous lecture 20, the function, in this case, the scalar, is the inner product we derive gij ui vj. And we also showed that dc of dt is equal 0, where inner product is conserved along the geodesic. So this is from previous lecture 20. Then C, now applied to the spherical surface, this g theta theta, u theta, v theta, g phi phi, u phi, v phi. Attention now, u theta is 0 according to previous lecture. You see? So this term here will be 0, and this leads to C is equal sine square of theta times 1, you see u phi is 1, and v phi is phi dot. You just look at here, you see, this is a phi dot. You see, this here is v in this case. Let's go. Phi dot is this one. You see, this one's a phi dot. You see, I just wrote here. So this is sine square 1, and phi dot is this case, okay, is phi dot c square theta. So this is a capital C, which is constant, you see? So dc of dt is equal to 0, as we showed in lecture 20. Now, the physical interpretation of this relation here, okay? So you have the z-axis, okay? This is theta, okay? Theta, you see, is the polar coordinates, and phi is azimuthal coordinates, you see? This is phi dot here is the rotation, okay, for some theta, okay, around the z-axis. So this is this case the angular momentum, okay. Lz is the component of the angular momentum in the z direction, you see, because in this case, this particular case, it's moving, okay, around the z-axis, see, as this is a component Lz. Now that's good just to say something about what have been done. So these conserved quantities correspond to the component of angular momentum associated with rotation. Rotation, which rotation? Rotation around the vertical z-axis. Since Killing vector field, this is a basis vector, okay? This partial phi generates azimuthal rotation. Attention, symmetry of the metric. The associated conserved quantity is the z component. You see, this is Lz here. You see, this is this case of angular momentum. You see, on the right hand side is the angular momentum that's represented by L sub z. In the intrinsic geometry of the sphere, you are working in intrinsic geometry, okay? That's important here. So this is important to repeat that. In more general terms, Killing vector generates isometries and their contraction. Contraction with what? Contraction with the geodesic tangent vectors, V. Yield conserved quantities via d of dt. This is this case the inner product. This is equal to 0. So that's important, because here it's emphasized that Killing vector, okay, needs geodesic, okay, to lead a conserved quantities. They work together. See, but Killing vector does not necessarily need the geodesic, because if it involves a geodesic, then the result, this leads to the conserved quantity. Okay, that's it. Because they work independently, you see. But if you join Killing vector and geodesic, then we obtain, in this case, conserved quantity. That's good to emphasize this.